Can you hear me? Good evening, everyone. Can you hear me? Can you hear me? Hey, everyone. Can you hear me? Okay, fine. The books we can refer here or Sadiku, right? So that you can have the quality questions for the practice. Let us start. So, why we study network theorem? There are many theorems which will help us to simplify the circuit analysis. I mean to say greatly simplify the circuit analysis. That is the reason we study the network theorems. First we will look for the first theorem we will discuss, that is your superposition theorem. Superposition theorem is the direct result of linearity. For a linear network, response of the network, response means either node voltage or branch current. Response of a network or circuit due to many independent sources can be found by considering each source at a time and reducing all other source sources to zero, leaving their internal impedances. Leaving their internal impedances. And finally adding individual responses algebraically. What it says, superposition theorems, what it says, if you have been given a network and you want to find the response of the network at any point, it can be found by considering each source separately and reducing all other source to 0. Then add the individual responses algebraically, that is taking into account sign. So if you have voltage source, when you reduce the voltage source to 0, voltage source replaced with its internal impedance. So ideal voltage source has the internal impedances of 0. So voltage source will be replaced with the I mean to ideal voltage source replaced with short circuit, and ideal current source, आपको करंट सोर्स को रिड्यूस कर देना, सोर्स रिप्लेस्ड विथ ओपन सर्किट. Clear? That means if you have a voltage source, make it short. These are the independent voltage source. If there are linear dependent sources, then you need to keep them active sorry, in each experiment. Right? So if you have any dependent sources, you need to keep them active. One second. So we'll discuss one example. Three ohm, 6 ohm, this is the 2 ampere current, and this is your 6 volt. We need to find I. So first let 6 volt source is active. So circuit becomes, because as per the superposition theorem, you need to reduce all other source to 0. So ideal current source, so it will be open. So your current due to voltage source only, current due to voltage source only, you can easily see that 6 upon 9, that is 6 upon 9, so that is 2 upon 3 ampere. Let 2 ampere source is active only. So the circuit becomes, the voltage source will be short, never change the orientation of the current, because they have asked the current in this to downward orientation. So this is the current due to the current source. So if you apply the current division, this current will be 3 upon 3 plus 6 into 2 ampere. This is a current division. So this current is the 3 upon 3 plus 6 into 2, that is 3 upon 9 into 2, that is 2 upon 3 ampere. So the response, that is the current, when both the sources are active, you have I of V, I of, that is 2 by 3 plus 2 by 3, which is 4 upon 3. Here whenever, if you can understand, you can definitely ask in the chat box. So let us apply the with a dependent source, that is the your superposition theorem when we have a dependent source. The question is, Ti, this is your 7 amp, then 3 ohm, 2 ohm, this is your 24 volt. What is the value of I? There are many ways to find the I instead of applying the superposition theorem, but we will discuss through the superposition theorem. Let us make only 24 volt active, because as per the superposition theorem, only dependent sources can be reduced to 0, right? Dependent, so I mean sorry, as per the superposition theorem, only independent is equal to 24. Okay, yeah, CI, okay, 24. So I equal to 24 upon 8, which is 3 ampere, and this is I due to the voltage source, so I can designate as IV, that is 3 ampere. Right. So now make active 7 ampere current source and reduce the 24 volt to 0. So this will be short, 24 volt will be short. dependent source should be always active, right? So this is your 3 ohm, 2 ohm, 7 ampere. This is the current I. See, I am not changing the current due to the current source. So orientation should be, or direction should be, remains same. So I can easily apply, let this is your V. So I can easily apply a node equation. So node equation will plus 7 equal to this current. This current is equal to this current. What is this current? V minus T of II. Okay, 3 of II, which is equal to 2, right? So you have I multiply by 2, 2II plus 14 equal to V minus 3II. And you see that, what is the V? Can anyone tell? So V is simply, from here you can easily see that V is equal to minus 3II. So put these values also. So 2II plus 14, which is equal to minus 3II minus 3II. That is 3 plus 3 6, then plus 8, 8II is equal to minus 14. So II is equal to minus 14 upon 8 minus 7 upon 4, right, which is minus 1.75 ampere. And the total current, when both the independent source, that is 7 ampere and 24 volt, are active, that I you need to add algebraically. So I due to the voltage source plus I due to the current source. So due to the voltage source it is 3 ampere, and due to the current source it is minus 1.75. So 1.25 ampere. This is the answer. This question you can also directly do by applying the KCL. Applying the node equations. So because I need to show about the node, and that is superposition theorem. So I have displayed the how you need to apply it. Let us move to the next theorem. So next is the pair of theorems, that is the node Thevenin's theorem. It's the most used, and also it's dual. It is your Norton's theorem. So any linear network, okay, this is a linear network. Any linear network can be can be replaced with a voltage source. So I can write these networks as a voltage source VTH and a resistance RTH between A and B, right? That means a voltage source and a resistance. This is a linear networks, and these networks can be represented at the terminal, open terminal A and B. Open terminal, this is the open terminal. What is the VTH? VTH is the open terminal voltage VAB. And what is the RTH? RTH is the resistance looking into the or impedance. For example, if it is a AC circuit, so you can, yeah, good evening Harsha. If it is AC circuit, impedance, so resistance looking from open terminal A and B into the network, okay. So, and at that time you need to you need to reduce the independent current source to 0, while reducing independent sources to 0. Okay, let us go through the example. Find the Thevenin's equivalent circuit at A and B, find the current through it. Okay, so it is a circuit given as like this. Five ohm, 20 ohm. It is a simple thing because this is the most basic circuit. So find the Thevenin volt, or you can say reduce the circuit, reduce the Thevenin's equivalent of the circuit at the terminal A and B by removing the load RL. Okay, that is, first you remove the RL. How to reduce the terminal to the, that is the how to reduce the circuit into the Thevenin equivalent? First you remove the load. This load can be linear, non-linear, anything, okay, but circuit need to be linear. The circuit which you are reducing to the Thevenin equivalent has to be linear. So you cut here, cut the load, okay, and then find the open circuit. Now it is open. When you cut here, Now this is open. What is the open circuit voltage? When it is open, this side current is 0 and only current flows through this is the I. So I is equal to 50 upon 25, that is 2 ampere, and this voltage VTH is the simply voltage drop across 20 ohm resistors. So VTH is equal to 20 into 2, which is 40 volt. Source you reduce to 0, so voltage source reduced to short circuit, because this is an ideal voltage source. And what I have told you next, find the resistance from open terminal A and B looking into the network. Looking into the network, you stand here and you look, okay, you look to the network. So RTH is equal to 5 parallel 20 plus 4. So 5 parallel 20, 100 upon 25 plus 4, that is 8 ohm. So now the circuit is reduced to a simply a voltage source and a series resistance RTH. This is your 40 volt and this is your 8 ohm, and this is your A and B. This is the Thevenin equivalent of the circuit. Now connect your load 2 ohm. So the current through the load IL is equal to 40 upon 10, which is 4. This is a very simple example. So any sort of the circuits, you can reduce it into the Thevenin equivalent circuits. Okay. Suppose you have a network. I have told you that when you have network of independent voltage source or current source, you can easily reduce to 0 and find the equivalent resistance like this. It is damn easy. But what happens when you have dependent sources, linear dependent sources? Okay, there are 2 to 3 ways. Primarily we discuss the first one and 2 will discuss. One is we calculate the VTH, that is, what is that? VTH here, open circuit voltage, right? Open circuit voltage. Similarly, you have been given network. First case is this is the network. You have dependent sources. So you have A at the terminal A and B. First you calculate the open circuit voltage. Then connect a short between the A and B. Short the A and B. And this will be the ISC short circuit current. So your VTH will be the open circuit voltage upon ISC short circuit. Right. Second way is the most widely used to find the because whenever you are analyzing the analog electronic circuits, okay, you will come across many dependent sources like GM, VGS, okay, beta IB, GM1, GM2, VGS, VDS, like that. So at that time, what is the convenient is the network in one go will just connect a voltage V2 and drive with the I2. What we do before doing that, in this case nothing has to be done, that is, don't reduce the voltage of 0, anything you need to change. But in this case, first reduce all independent source to 0. That means ideal voltage source short, ideal current source open, because infinity impedance. Now, oh sorry, ZTH na, ZTH or RTH. Okay. So now in the second case, your RTH or ZTH is equal to V2 upon I2. Right? Yeah. Harsh, I have amended it. Okay. Another easiest case normally people follow, normally rarely follow, but it is one. Simply network, reduce all the voltage source, independent voltage source to 0. Reduce, okay, reduce all the independent voltage source to 0. See the magic here. Drive the network with 1 ampere current source, and this measure the V. So your JTH same V upon I, but here I is equal to 1 ampere. So ZTH is numerically equal to, this is the easiest one, but people, students rarely use it, okay, but you can have a practice about simply this method. Let us discuss through all the three forms of finding the Thevenin resistance you studied. So let us discuss the example. Okay, example, and then practice. You need to practice. Then only you will be mastering in the application part. So let us have, you have been giving this circuit. This is the 20 volt. Usually many questions comes in the from the Thevenin's, that is the network theorems, in the GATE exam, engineering service exam, any exam you sit, you will find the question based on the network theorem. And that is not only criteria to study network theorem. If you want to use the you want to analyze the circuit in a multidimensional way, you need to have all the weapons with you. So network theorem sometimes greatly reduce the efforts for the solving the questions. This is a 6 ohm. This is a dependent source 2I, and this is the I. Okay, this is your 10 ohm, and this is your 6 ohm. Thevenize. Okay, we need to find Thevenin equivalent or Thevenin parameters. Thevenize above circuit. Thevenize above circuit. at AB. So first is the straightforward, that is the VTH, because no current flows through the 0 ampere. So apply a KVL around this loop, because this current will flow, this is also I. So apply the KVL around loop. So 6 of I minus 2 of I plus 6 of I minus 20 equal to 0. So 10 I is equal to 20, which implies I equal to I equal to how much? That is 2 ampere, and the VTH is equal to, okay, VTH is equal to, that is no zero current flows, that is the voltage drop across the 6 ohm resistors. 6 into 2, that is 12 volt. Right? Now we will find the Thevenin resistance. For Thevenin resistance, we will redraw the circuit. There is a dependent voltage source, it reduced to the 0. This is the 6 ohm, minus plus 2I. Don't reduce the dependent source, or don't disturb the dependent source if any. Okay, here dependent source is the, what is the type of dependent source? Current controlled voltage source. The current through 6 ohm resistors determines the value of voltage, value of this voltage source, 6 ohm. Okay, and this is your I. So what I will do, I will use the third one, is the easiest one. See, first one, if you sort here, first method, like I have told you, see here in the first method, that is the short circuit current. Okay, if you sort, then you will find the current, because the current through this is I, then another equation, that will take little bit of time. So that's why I told you all the method you should know, and which one should best you should apply in the exam. So I put 1 ampere current here. So 1 ampere came, okay, one, oh, 10 ohm resistors is there, na? 10 ohm, and this is your V. So V is equal to, this is the 1 ampere is coming, this is 1 ampere, so this is 1 minus I, this is your 1 minus I, right? 1 minus I. Now apply the, first you apply the bigger one, smaller KVL, that is the V is equal to 6 of I plus 10, because 10 into 1, 10, equation 1. Now apply the KVL around, because there are two variables, we have to, we need two equations, so we need to eliminate one. So then apply through the KVL through this. This is the your traverse. So 6I, this way I am traversing. 6I minus 2I, current is flowing in this direction, minus 6 into 1 minus I equal to 0. So 6I minus 2I minus 6 plus 6I, okay, plus 6I equal to 0. So 12, that is the 6 minus 2, that is a 4, 6, so 10I is equal to 0.6. 0.6. So your V will be the 0.6 into 6 plus 10, that is 3.6 plus 10, that is 6.4. So this is your Thevenin resistance. RTH is numerically equal to V, that is 6.4 ohm. Okay. गलती हुआ है कहीं 0.6 13.6. So RTH is equal to 13.6 ohm. So you can write or you can draw the equivalent circuit with the application of Thevenin's theorem. So above circuit can be reduced at the point A B as like this. The voltage source was the 12 volt and this is your 13 point. Very simple and very easily we could find. Now let us move to the Norton's theorem. As I have told you, Norton's and Thevenin's are dual of each other. Norton's and Thevenin's are dual of each other. That is the simply do a source conversion. Simply do a source conversions. Whenever first discuss the what is the Norton's theorem. Likewise, in case of Thevenin theorem, same way you have a linear network here. This is the terminal A and B. You can reduce it into a current source and call that is Norton current, and a resistance parallel with the current source, that is the Norton resistance. Like Thevenin voltage, Thevenin current, you can reduce into the this at the terminal A and B. What is the Norton current? IN is the short circuit current at AB. Short circuit current at AB. That means you have a network. This is A, this is B. Put a short, and this current is your IN. And what is the RN? RN is the same you are doing for the Thevenin resistance. Looking into the network, which is RN. There is no change. Right? That means there is no change in measurement or calculation of the Norton resistance. It is same way as we are doing for the Thevenin resistance. In fact, Thevenin resistance and Norton resistance are same. So as I have told you before, they are dual of each other. Suppose it's a Thevenin, Norton. If Thevenin has been given, then you can simply add within fraction of minute. Okay, you can simply represent with a current source. The value is Vth upon Rth and resistance which is Rn, which is simply Rth. That's all. And this is AB and this is A. Hope it is clear. Okay, I needed to discuss about the how to calculate the actual equivalent circuit once, or you can, if you have given the Norton's Norton equivalent circuit, then you can easily find out the Thevenin equivalent circuit. Sometimes you will have the it may be difficult to find the Thevenin equivalent circuit, but it is quite easy to find the that is your Norton equivalent circuit. So Thevenin and Norton. Okay. Let us do one example as we are discussing for the Norton. In the next class, we will discuss the at least 5 to 6 previous year GATE question. First learn the basic, then you revise, then practice some questions with the previous year GATE questions, then we will discuss the. Otherwise, if you don't revise, if you did not revise, then doing the questions, it will not be helpful. Find the Norton equivalent circuit at A and B. At A and B. So you see here, you can easily when you sort it. Okay. Now I sort here. This is your Norton equivalent current. That is a Norton current. So you see that what is this current? Because when I sort, the potential here same, here same, right? So if the potential is same, so this terminal is connected to this terminal. So this current is the 24 upon 4, that is 6, and this is the 3 amp. So 6 amp, then 3 amp, all are going through this short circuit. So your IN is equal to 6 plus 3 is equal to 9 amp, right? So, and Norton resistance, this is open, this is open, this is short, that is 12 parallel 4 ohm, that is 12 into 4, that is 16, which is 3 ohm. So now the Norton equivalent circuit IN 5 नहीं, this is A and B, this is the Rn which is 3 ohm and IN is equal to 9. Clear? So quite easily you can do. So next theorem, we'll discuss the previous year GATE question in the next class. Reciprocity theorem. Questions are keeps coming from this theorem also. Reciprocity theorem is applicable to linear bilateral networks. Now question arises, you know linear, okay, linear you know that is circuit composed of linear elements like linear resistors, inductors, capacitors, all are linear element, also dependent source linear nature. What is the bilateral? Bilateral means the characteristics, suppose you have a network here, you connect the positive voltage V and you are getting the positive current, and suppose this network is, and you know that is your V upon I is, let us say some value, a constant. Now suppose you reverse the voltage, like this ratio and this ratio should be same. Let us say I designate as the V1 I1 and this is the V2 I2. So that means V1 I1 is equal to V1 upon I1 is equal to V2. That should be same. Okay. What are the non-bilateral? Simply diode. Diode is a non-bilateral. Your transistor non-bilateral. Okay. Diode, you know the diode characteristics. This is the this and so they are not equal in reverse direction. But resistors bilateral, capacitors bilateral, for resistors bilateral V and I, for capacitors bilateral. Okay, always remember passive network is linear if they are made up of linear element. Then so obviously in the network theory we are discussing only linear element. So passive network is always bilateral. Even reciprocal also, that will be discussed in the your that is in two port networks, symmetrical networks, then your reciprocal networks. Passive network is a reciprocal network also. Okay, so in the reciprocity theorem, what it says, just understand, you have a linear bilateral networks, okay, and source free. Source free. Source free it is, then always bilateral network. If source is there, it may be bilateral, non-bilateral. Okay, so broadly we are talking about the linear bilateral network. Suppose you have an impedance here. Okay, you have an impedance here and you apply the voltage, let's say V1. Okay, V1, this is the port 1 and this is the port 2, and another impedance, let's say it is Z1 and Z2. Now you measure the response, let's say I2, response current. So find the ratio, right? Now interchange response point and the source. Same linear bilateral network. What I did now, I interchange response point and let's say I1, because port 1 Z1, I interchange the source and response taking point, and this is your V2. I took the ratio V2 upon I1. So according to reciprocity theorem, V1 upon I2 is equal to V2 upon. What it says in simple words, the ratio of voltage, that is the source, and the ammeter reading of the other port will be same if source and ammeter are interchanged. This is the simple definitions of the reciprocity theorem. So don't, in that case, don't solve the circuit, just identify whether this network is the qualify for the linear bilateral network or not. For example, circuit is given, a complicated circuit has been given, okay, like this, and let's say that this is a network, and let's say this is the 2, this is your 1 dash, let's say 5 ohm, 10 ohm, 12 ohm, 13 ohm, 14 ohm, right? Now they give that when a voltage source they connect, it can be current source. Okay, don't confuse that, sir have taught the voltage source and it has been given current source, and a series resistance is there connected to the 1 dash, and they measure the current here. Another resistance here, let's say this is R1, this is R2, and they measure current, and they are given that V2 upon I2, let's say they designate like this, let's say I2 is equal to 5. So what is the ratio of, they may cleverly put that voltage source in terms of current source, but resistors, when you add the resistance, that it will be same scenario. Then you can easily write, for example, let's say here they give you 5 ohm, okay, and they here they give you the let's say here 3 ohm, okay. Now they connect the, let's say it is 10 volt. Now what did they connect the here another circuit, let's say same network, same network, okay, same network, 5 ohm, then current I1. What it did there, here you just see 3 ohm there. Now the current source of 2 ohm, and voltage source of let's say you have 3 ohm or 3 volt. They will ask what is the ratio of V2 upon I1. V2 upon I1. That 3 ohm was there, na? Okay. Okay. They'll just because reciprocity theorem, for the reciprocity theorem it should be same, na? 3 ohm. Here 5 ohm, and same network. So the V2 upon I2, because V2 upon I1 is the 5. So as it has been changed to this. So V2 upon I1 will be also V2 upon I1 will be also 5. So they may ask what is the value of I1. I1 will be the V2 upon I1 V2 upon 5, that is 3 upon 5, which is 0.6. Very simple. Just remember the situation remains same for the both the side. Then only you can easily correlate for the superposition theorem. So once again, I want to, if you have confusion, if you have a network here, okay, network which is linear and bilateral network, you have been connected with a, let's say this is R1 and another is the R2. What it says that is, if you connect here, let I designate as the, this is R2, just check, you just remember it, R1, then here I measure the I1 and here I apply the forcing function V2. So that ratio is the V2 upon I1 also same. Hope it is clear for you. So in the next class we will discuss about the another important theorem. Every year you will find the questions directly or indirectly, that is the maximum power transfer. Okay. There are other theorem also, Telgen theorems, then another one is the compensation theorem. They are not so important. We will just mind the all these two theorems are there. When one theorem is left, that is the maximum power transfer. So you can easily do it. 3 theorems are actually important. 3 or 4 I think, though that is your superposition theorem. Sometimes they will give the large number of sources, so you can easily correlate. But first you look at the questions, okay? Just don't blindly jump into the some theorem or like that. Just look at the sometimes you need not to calculate anything. Just put a KCL. You will easily find out the answer. You may be finding the current is flowing through the some resistors, and you can simply multiply and to get the result. Okay. So there are a lot of questions they are asking in the competitive exam. Not only questions, for example, you want to analyze the analog circuit questions, then you need to study well the network theorems. Okay. So with this we end the class. Please be serious for your study. It may seem that you learn everything. Sometimes you may not be knowing the fine line of the any conceptual things. So please attend regularly the class, those who have registered for the our online classes, and participate, because I am regularly sharing the questions. I request you all to participate for the question discussions. Don't keep your mind or keep your brain idle. Just run it and put effort, put stress to your thought process, and definitely you will be my aim is to develop the problem solving ability and stress taking ability. So this is a long process which you have skipped in your 4 year of engineering, because normally people thinks that once we are in engineering college we will be passed out and we will get a very good job in the software industry. But nevertheless you need to study, and that part is missing from you people. That's why you are here to learn the conceptual things. Though network theory, you are well at the network theory, but definitely some topics you may not be, you may be thinking you are well versed, but like your transient analysis of second order system, that is the initial rate of change, then some two port network concept. Many people are confused with the two port network. Okay. Please hers and no one is commenting, so I can tell about the hers. Please you follow it, and definitely you will be your dream will come true. Definitely you will be reaching the your desired destinations. Put your best effort, practice, and get the success. With this we end the class for the day, and see you not tomorrow. Tomorrow I have some work, and the Dheeraj will take class, the mathematics class, and we'll see day after tomorrow. And after the network theorem I am planning to start with the devices. Okay, that means we should alternate day, one day device and another day network theory, and then we'll continue whenever anything finish fast. That most probably the network theory will finish fast, so we'll start the analog. So we'll not wait for the end of this network theory and start another subject. That may be taking a lot of time, and also learning one subject may be boring for me. It is my personal experience. If I keep studying only one subject, then I feel bored. Sometimes I feel that I should not, I will not study this subject, one single subject. So for me, two to three minimum three subject I used to prepare, so that I have a different test of that is concepts. Like you know, three subjects are related, this network theory, signal and systems, and control systems. But I don't want to take the related subject first. I want to try the device, because this is very much important, and that once you master it, then definitely it will be a catwalk only. Device also very much important for the, if you are opting for the VLSI course. Though you may be thinking that I am from electrical but I am interested in the VLSI design, then many people are misguiding you. Okay, understand, many people are misguiding you in the YouTube video, that if you are electrical computer science, device is not required. If a device is not required, if you don't know the characteristics of a device, how will you design a circuit based on the device? Suppose you don't know how it is on, how the MOSFET is on, how the MOSFET is off, how the conductivity of the MOSFET varies, how the threshold voltage of a MOSFET varies, then how will you put that parameter into the action? So don't be trapped in the misguidance that I will not require the device subject. I will not require the, if you are going for the digital VLSI, you will not study the analog VLSI. I mean to say, you must be multidimensional. See, you are squeezing already. You are a electrical engineer. Okay, electronics engineer. You study a lot of subjects like power electronics, communication engineering, control engineering, your signal digital signal processing, and your analog electronics, digital electronics, device theory. Now from all these subjects you have squeezed to the VLSI design, like only device, circuit, all these things. You have left altogether your communication engineering, signal processing, okay, control theory, control engineering, that is also a very vast course, power electronics. Now you want to reduce again into the only digital VLSI. Don't you think it is myopic view? You must be ready for the all the things coming into your domain. I mean to say, all the thing in your field, device field, all three has to be studied equally. Okay. With this we end the class. Keep reading, keep learning, and explore the new way of learning the electronics. Thank you. Good night. Please subscribe and tell your friend to subscribe this channel, and they will learn a lot of new things and they will improve their knowledge base.